0.3 slope sounds like what it is. It's a graph of a bunch of slopes. That's all it is. So, but what's nice about these is it gives a way that you can see what your actual solution is to a different. Make that we can see better. All right, so in other words, this differential equation, this says dy dx equals y. If you go back to the beginning of the course, when we first started doing derivatives, I told you it's not a big deal. All a derivative is a slope. So what this is this is the, in other words, the slope of this graph is whatever the y-coordinate is. So if the solution goes through the point 0, 1, then the slope there would be 1. If the point goes through y equals 4, then the slope there would be 4. So whatever the value of y is, and so I could look at a graph and, yeah, so we can see the blue lines. I could look at a graph here and kind of ignore the blue lines, and I could draw a little line that is actually, this is the slope of 2. You can see this is steeper. Okay, and so in other words, wherever I'm at this point on the y, that would be my slope. So 4, 8, and so on. You okay? All right, and so in other words, the slope at point 02 would be 2 because y equals 2. All we're really looking at is the y values. And when I draw this line, I don't even know, have y'all ever seen a program that will do this for you?
The TI-89.
No, I meant like on the computer that you could print it out. That would be, maybe we should invent one. You have?
There was a website that she said
that you could use to do these. Okay, we'll try to find that for those of you that have to do this. All right, because basically what I would say is draw the slopes maybe in quadrant 1. Well, I mean, in other words, you're going to draw slopes of 1, 2, 3, 4, 5. And so this is what a slope field looks like. I guess I am glad the blue's showing now. So if I just look at these at y equals 2, all of these are lines with slopes of 2. If I look at y equals 1, notice the slopes are going down a little bit because it's not as steep as 2. So slopes of 1. Of course, if I'm at y equals 0, may be hard to see, but there's actual lines there. That's your horizontal slope. If I'm at -1, now my slope's going down. If I'm at -2, my slope's decreasing faster. So what you end up doing with things like these, well, if I drew many and many of these, is what's called a slope. And you get to a point where you say, okay, in this case, if I'm looking at all of these, I have positive slopes because my y is positive. All of those are positive lines. Once again, there's my 0, and then they become negative. And this is the slope field for this differential. As the slope increases, of course, as y increases.
What if it's you don't indicate there's a straight line slope? Right?
Vertical? No.
No?
Yeah, no.
Okay.
Differential equation wouldn't exist, right? You'd have a vertical line. Yeah.
Because I always got that wrong last year.
And so then we have, again, our of course, below we have our negative. They call this a ghost of a solution curve. What this means is, here is your differential equation. I want you to find the solution just by looking at it, and you go, can't do it. You could graph all these slopes here. Let me get a color that shows up. And you could start anywhere, like an initial population or something, and you could start following these lines here, and you would see right away that looks exponential, doesn't it? And so even if I started over here and I continued to do this, I'm trying to hit the lines, I promise. It looks exponential. So this is what they mean by a ghost solution. You could kind of see what the original function is here. And this gives me that exponential shape where y equals e to the x would be a solution to this differential equation. It would be a solution. Okay, this isn't going to give you always the perfect solution. Oh, I got a clock up there now. And so what I could do is set this up and say, well, as Ben mentioned earlier, this is going to change my constant depending on my initial amount. And so I could just throw that constant out front. There'd be nothing wrong with doing that. And that says that this is still a solution to this. And so I could check it. How could I check it?
Doing it by hand.
Say that again?
Doing it by hand.
The derivative, yeah. So in other words, I had dy dx equals y. I have y equals c e to the x. What's the derivative of c e to the x? CE to the x. So in other words, y equals CE to the x. Plug in my y, that's my derivative, and it looks like the two sides are equal. So that's all you're doing with these. You could either start, might have been easier to start with that and say, okay, plug in the derivative, plug in your original function. Are the two equal? If they're equal, then that is an actual solution. All right, so if I have this example, 2x, and once again, these are my, and so I actually go through and graph them, and this takes a little while to get used to what's happening over here. So if I'm looking at all these different values here, and I'm graphing, I'm going to tell you just now that the solution to this is x squared. Well, most of you could see that, right? Because if you do your antiderivative, if you took the derivative of x squared, you're going to get 2x. So that one's pretty easy, right?
So you just separate variables.
Yes.
That's why I like math better than
Yeah, that's true. And so in your homework, what they'll ask you is they'll say which slope field corresponds to which differential equation. So here's this one. Here's this one. Let's call this A and call this B. Which one goes to number 1 and which one goes to number 2?
I think number 2 is B, A is 1, I think.
So what I would have to do, and again, it might be certainly over there hard for you, is I would go through here and I would start looking at slopes. So in other words, I know at 2, my slope is 0 because 2 minus 2 is 0. So again, you know how Wiley is, doesn't give you numbers, but pretend that's at 2. And so I would have all of these would be straight lines. Okay, those would be my slopes. If I go up 1, meaning to 3, then I'm going to start going negative, right? Because if this y is getting larger than 2, that's why all of these slopes are negative. If I'm going below it, so in other words like 1, then I start to see all of these positive slopes. So what I do is I pick one of these to kind of see what's going on. And notice in this case, this t is my t-axis. So here, something like this, I would see, well, if I'm at my t of 1, and again, might be kind of hard to see, if I'm at 1 here and my y is at 1, then I know my slope's going to be 1. So that's kind of how you look at these to figure out which one of these goes.
Oh, I can figure out that 2 is to be.
Looking at the 2, the 0, that's what I look first, is I look for the 0. I think that's the easiest way to do these. Okay, and so you can also look at these with actual initial conditions. So in other words, if I say when y equals 1, 0, my initial condition, well, in other words, that's saying here, if I start at t equals 0, so here's my t value of any of these, and I look at 1, which is right here. What I do is I start sketching my slope fields. I can do it for the different ones. I can go up to 3. And again, it's kind of hard to see. These are so small, but I'm just sketching a line. I'm following my slopes is what I'm doing. And then I'm sketching a line to see the different solutions. Well, why, you might look at that and say, well, there's a whole bunch of different solutions. Well, think about exponentials. If you have negative values in your exponents, then it starts to come down. If you have positive values, and so a lot of this is dependent on what your constant is.
So if on in our test, if we had if you wanted an initial point, we can say anything as long as it hits that point.
It hits that point. Yeah, you could start from, exactly. You could start from, because sometimes it's easier to see. Yeah, sometimes it's easier to see. I don't know, some students kind of have trouble with these of following, I guess because there's so many lines,
I had this at the exam. They said that you can choose anything
as long as you go through that point.
The slope corresponds to it also.
Exactly, yeah. And what would be easier is if you knew those values. And then, of course, over here, if I'm looking at the second one, I'm doing the same thing. What Justin is saying, so in other words, I said when t equals 0 and y equals 1 is that point. What he's saying is, could I start over here as long as I hit that point? Of course you could, and that's usually easier because you can kind of see this pattern here. When you start here, you're kind of zoomed in, and it's hard to see, well, where is this actually going? Okay, to be able to draw these. All right, and so of course I can look at these solutions and I can see at each one of these, it looks like both of them are getting very, very close to a value, Well, if you notice, this one kind of makes sense, you know, that it's getting very, very close to that. So, sorry. And so, in other words, all the solution curves have y equals 2 as a horizontal asymptote, so it doesn't matter what your constant is. And so what we were saying is y approaches 2 as t approaches infinity, as I head way, way out here. In this case, this is my t over y with my initial conditions. I see what's happening with my y is actually heading out to infinity as my t heads out to infinity. So in other words, it tells me what my asymptotes would be in this case. So this might be a scenario, both of these, what's happening in the long run. And that's another reason why you like slope fields. But the bottom line is why you like slope fields is, and probably not that one, is you can look at these and figure out a solution that maybe you couldn't have just figured out by looking at your differential equation, okay? And so that's kind of the use of them. And again, this is something we're going to do an exercise because it's kind of like graphing derivatives. Most students have trouble with it. And I need to make sure a few of you guys can do these because, again, they're in your projects.
So basically,